Yeah, the presentation is visible.
Okay, so I just stopped my video so that there is no internet issues. So thank you once again. A very warm good morning to all of you. So I'm Chinchu Cherian, and I'm now connecting from Canada. So it's around 9:30 p.m. here. And I'm so happy and I am delighted to be with all of you today and present, a small topic, which is recent advances in stabilization of contaminated soils and hazardous industrial waste. So before we go to the contents of the presentation, I'd like to just begin by saying this word of Dr. Charles E. Kellogg. So essentially, all life depends upon soil, and there can be no life without soil and no soil without life because they have evolved together. So these are the words of Dr. Charles E. Kellogg. He was a soil scientist and chief of the Bureau of Chemistry and Soils at the United States Department of Agriculture. So as we all know, soil is the most important treasure that we have. It's the most important resource that we have, and it's our responsibility to take care of soil and to protect it. So let's move on. This is a presentation outline. So we'll start by just discussing what is soil contamination in general and what are the different types and sources of contamination. And I'm pretty sure there may be some overlap because we have had a few other talks before, and I'll try to make it simple as much as possible. So further moving on, we'll also look at some of the basic and advanced solutions to soil contamination, especially how they work and what contaminants are amenable for each type of the soil contamination remediation techniques. And we'll also look up at some of the limiting factors of these techniques. And most importantly, I want to discuss with you some of the hot research topics in the area of soil reclamation, or the treatment of contaminated soils or hazardous waste. And finally, we will conclude by mentioning the key takeaways of this presentation. So to start with, so we all know what is meant by contamination. And when it comes to soil, we also call it as soil pollution. So it's basically the buildup of the chemicals or radioactive materials, toxic compounds, and disease-causing agents in the soil. And when this accumulation or the buildup of the various chemicals or toxic elements go to levels that can cause adverse effects on plant growth and damage to both human and animal health. So that's when we call that a soil is contaminated or a soil is polluted. So sometimes these chemicals or radioactive materials may be naturally present in soils, but they are not available up to the level of contamination. So when the levels goes beyond that is permissible, we call it as a contamination or pollution. And the contamination of soil can be caused either by natural activities or by human actions. Excuse me. And this can destroy the soil properties, such as the soil structure and composition. So when we talk about soil structure and composition, we talk about the mineralogy of the soils and about the chemical composition of the soil, and also the soil biota, that is the living organisms or the living matter present in the soil, that also get disturbed when the soil is polluted or contaminated. And when we talk about soil contamination, we first look at the sources of contamination. So what are the different sources that can lead to a soil pollution or soil contamination? And as you can see in this figure, so this is just a simple figure. This is taken from one of the research papers from Zauza et al. 2020. So here we can see that there are some major sources for soil contamination. That is basically, it can be due to some agricultural activities. Okay, so agricultural activities, one is the first major factor that can, or the source that can lead to soil contamination. And when you say agricultural activities, how does it cause soil pollution? So basically, the addition of fertilizers. Okay, so the practices such as adding fertilizers, pesticides, or herbicides, and fungicides, so all these kinds of harmful chemicals can lead to soil pollution. And when I say harmful chemicals, some of these fertilizers or pesticides can have toxic elements or metals such as cadmium, arsenic, lead, etc. And these gets transferred from the fertilizer to the soil and later on to the plants, and it enters into the food chain. And most of these toxic metals are non-biodegradable, and therefore it's very harmful. Excuse me. And then we have the industrial sources. That's another major area or major source for soil contamination. So when we talk about industrial sources, the industrial byproducts and waste materials. For example, we can take the example of a paint industry, or even any industry which produces or generates harmful byproducts or residues as a result of their activities in the industry. This can lead to soil pollution, especially, sorry, excuse me. So especially when these kinds of chemicals or residues are discarded into the surroundings, okay, that can lead to pollution of the soil. And most of the times when these chemicals or byproducts are discarded into the soil, they will be present in the soil at very high levels, and which is not admissible. And furthermore, when these byproducts combine with rainwater, it can cause acid rains. Okay, and this acid rains, what it does, it leads to high soil pH, and that can affect the overall crop production. And therefore, so that industry is dumping their solid and liquid effluents into the soil is one major source for soil contamination. Then further moving on, we also have the emissions from vehicles, also emissions from sewage and domestic waste, especially when we have municipal solid waste. These waste and the sewage sludges, when they are disposed in open dump sites, that can lead to soil pollution. So although these are the major sources of pollution, there are again some other important sources for the pollution. That is the nuclear sources. That is one major source of soil pollution that can lead to radioactive contamination of soils, such as uranium, thorium, etc. And then deforestation is another cause for soil pollution. So when we say deforestation, so we are basically talking about removal of trees in the forest. So when we remove the vegetation, it actually removes the protective layer on top of the soil. And this can also aggravate the situation of soil pollution. And we already talked about acid rain. So coming back to the industrial sources here, I just wanted to bring in some examples for industrial waste. Especially in a Canadian context, we consider mine tailings as one of the major source for soil and air pollution, as well as water pollution. So I don't, you may have already heard about mine tailings. So they are basically byproducts of an extraction process in the mining industry. It's a toxic slurry of residual and unrecovered metals. So it's a very toxic waste, And what they generally do, they make some ponds or containment systems, and they store these tailings in those ponds, and they treat the tailings to remove all the toxicity. And once the tailings are good enough to, to be discharged into a landfill facility or into a general sewer system, so until then they keep treating these tailings. And it's important to note that the management of tailing ponds is one of the most difficult environmental challenges, especially faced by Canada, USA, and the major countries which have, mining industry as one of their major industrial resources. So as you can see in this figure, this picture shows the growing oil sand ponds in Alberta, which is one of the provinces in Canada. So in Alberta, we have a lot of oil sand mines. So oil sand mines are those mines from which we, recover bitumen or oil. And it leads to production of or generation of this residue known as oil sand tailing. And you can see here in this picture how these tailings are mixing with the river water and polluting the water and the surrounding soils. Okay, so this is one example for an industrial pollutant. And moreover, it's not just the tailing itself, but sometimes the effluents that is leaching out of the tailings or these kinds of waste piles also becomes a source for soil and water pollution. As you can see here, this is a particular phenomenon called acid rock drainage. Okay, we call it in short term as ARD, or sometimes it's also referred to as acid mine drainage, AMD. So this is basically an acidic effluent which is generated from the waste piles or the tailings. And these effluents actually they leach over a period of time. They leach into the surrounding soil and groundwater, thereby polluting the entire ecosystem. And acid rock drainage is one of the largest environmental liabilities that the Canadian mining industry is facing. And as per the reports, the amount of acid producing mine waste in Canada is estimated to be about 2,650 million tons, which causes again an environmental liability of about $2 to $5 billion, which so we are talking in billions of dollars. So we already looked at the other sources of pollution. And I just wanted to share this beautiful picture. Again, it's taken from one of the research papers by Palan Surya et al. 2020. So this picture clearly shows, it gives the whole story of what are the different sources of pollution and how soil get polluted in different ways. Here we can see, let me get the laser pointer. Yeah, so you can see, some of the industries which are emitting, harmful pollutants into the air. So this leads to the acid rain and it comes back into the soil and it pollutes the soil. And then we have the effluents, like liquid and solid effluents getting into the soil. Excuse me. And here we have the agricultural activities. That's application of pesticides and herbicides. And then I'm so sorry for my cough. We also have the forest fires. So the wildfires, as I mentioned, is one of the major leading causes for soil pollution, again in Canada. And then we have mining activities, then animal manure application to soil. So, and it shows how these potential toxic elements releases into the soil and then eventually gets mixed with the groundwater. Now, so first we looked at the sources and types of soil contamination. And next important thing is to understand what are the different problems that the contaminated soils exhibit. Because as an engineer, when you want to really find a solution or a strategy to treat a contaminated soil, first of all, we should evaluate the soil and try to study the problems. So So here basically, as we saw before, toxicity is one major factor. So when you toxicity means especially the metals, harmful metals, such as cadmium, chromium, lead, and many more. So all these heavy metals are harmful to plants, animals, and microbial populations. So in addition to the toxicity, another important factor is the soil pH. So when a soil gets contaminated, its pH gets deranged. It can become too high or too low. Okay, and this can lead to soil infertility, because we know that a soil pH is an important factor which helps or which governs its ability to hold nutrients. So when the soil becomes too high or lower than the normal, it loses its ability to hold on the nutrients. Okay, and that's one another issue when the soil gets polluted. So what happens is when the soil becomes too acidic or too basic, many nutrients gets dissolved in water, and they are no longer attached to the soil, and therefore the plant availability of these nutrients gets reduced, and that can lead to reduction of overall crop production. So in an agricultural aspect, a change in soil pH due to contamination is an important factor. And then coming, we have excess sodium. So when there is an excess sodium in soil, that can cause toxicity to plants. We know that sodium is not a harmful metal, it's not a heavy metal, but still, when these types of metals go beyond the permissible limits, or the concentration of these metals go beyond a particular range, it can become toxic. And this can lead to a breakdown of soil structure and its dispersion properties. And as a result, this will limit the root growth, the aeration, water infiltration, etc. So we know that a soil needs to be properly aerated, like there should be proper air circulation and water infiltration through the soil for a proper support, to give a proper support to the plant growth. And likewise, excess salts like sulfates or chlorides, presence of these salts in high amounts also limit plant rooting, water intake, nutrient intake, etc. And a few other problems that are exhibited by contaminated soils are the change in its physical properties. So as an engineer, we are more related to, or we are more acquainted to the physical properties of soil rather than the agricultural properties. So when we talk about physical properties, basically we are looking at the density of the soil, its aggregation, that is, we call it as aggregate stability, like how strongly the soil particles are bonded to each other, and also the texture. So all these physical properties can be varied, or it can be altered by contamination, and as a result, this leads to a reduced water infiltration and moisture holding capacity of the soil. So the wildfire, I mentioned that wildfire is an important source for soil contamination. So when wildfire occurs, it basically burns the top layer of soil. Okay, and when the top layer of soil gets burned, that also lead to change in its physical and chemical properties. So when the soil gets burned, basically it loses its aggregate stability, and also it actually develops a repellency to water, and therefore it reduces the moisture holding capacity of the soil. So that's why we say that wildfires are a major cause or major source for soil contamination. And it's also important to know that sometimes some of the soils, when we want to do some agricultural activities, we look for the essential micro and macronutrients, right? So some of the important micronutrients in soils are like zinc, manganese, etc. So when these micronutrients are lower than the required limit, then we say that the soil is infertile. But at the same time, when these elements go beyond the permissible limits or allowable limits, they become toxic. Okay, so when the concentrations are too high, that becomes toxic to the soil. So sometimes when some of the pollutants that enters into the soil system has very high concentrations of these types of elements or metals that can become toxic to the soil. Okay, and another important factor is that so when you use some types of remediation methods for a contaminated soil, okay, for example, if you use a soil treatment method to reduce the phytotoxicity of one type of contaminant, okay, so that treatment method can cause an adverse effect by reducing the availability of another essential element in the system. Okay, so therefore when you use a particular chemical or a particular amendment to a soil to reduce the toxicity of one contaminant, we have to make sure that we are not causing any adverse effects on that soil. So in case it is going to lead to the decrease in the availability of another element, we must make sure that you add that nutrient as a companion fertilizer, or you have to supplement that nutrient in addition, so that you prevent the deficiency due to the particular treatment method. So these are some important factors that you need to consider when you choose a particular contaminant remediation technique for a particular soil. So now, so we talked about the sources in general. What are the different sources for soil pollution? And we looked at, what are the different problems that are exhibited by the contaminated soils. So now we can move on to the solutions. So how do we solve this problem of soil pollution or soil contamination? So there are actually a good number of incredible solutions to soil pollution, thanks to the people behind these technologies. But I would like to start. So before we go to those advanced technologies, I'd like to start with some of the simple solutions. Like we say, right? We always say like prevention is better than cure. So how can we prevent soil pollution? So we can just look at some of the simple ways to prevent soil pollution. So I have listed down some methods. One is reduction of artificial fertilizers and pesticides. Obviously, so if you reduce the use of these harmful chemicals, then the level of contamination can be naturally reduced. And then second is using or reusing and recycling of materials. So that is always a sustainable method. So if we can reuse or recycle some of the materials, that can help to reduce wastage. So it can help to reduce the amount of waste that is being produced. And in turn, that helps to reduce the amount of contamination in the soil. So when the waste production is less, then the discarding, the amount of waste going into the environment is less, and thereby the contamination is also less. And another important strategy is reforestation. So if we can add more vegetation to protect our soil, that can definitely reduce the amount of contamination. Further, so production of natural fertilizers is important. So these days we have a lot of organic compounds or organic fertilizers in the market. So they, at least they claim that they do not have any harmful or toxic elements in them. So if we can promote these kinds of natural fertilizers, or use of these natural fertilizers, we can obviously, or we can very well reduce the contamination to soils. And going for biodegradable products. So so when we talk about the toxicity, so the toxic elements, the main characteristic of toxic metals are that they are non-biodegradable. So they remain in the soil for like hundreds of years, and they slowly accumulate in the soil, and then they gets into the food chain and they affect the ecosystem. So the non-biodegradability is one of the main concerns. So if we can go for some biodegradable products rather than non-biodegradable materials, then we can reduce the soil pollution. Further, a proper hygienic condition and increasing public awareness and ban on toxic chemicals. All these are some steps that can be taken to to mitigate or to curtail the level of contamination of soils. So that's about some methods of or some strategies for reducing or minimizing contamination. Now, once we have a contaminated soil, then always our strategy is to find a proper solution or a remedial measure. Okay, and we have different soil remediation techniques available. Um, they are both in situ and ex situ technologies. So we can see in this figure here. So there are basically they're classified as physical methods or chemical methods and biological methods according to the type of the technique. So physical methods are mostly soil replacement. That is, when you have a contaminated soil, you remove or replace that soil with a fresh soil or a new uncontaminated soil. And another option is capping. So we can actually separate or cap or cover the contaminated soil by proper capping technologies. Like we can use some geotextiles or geosynthetics to cap or cover the contaminated soil and prevent further contamination of the surrounding regions. And then we go to the chemical methods. If you go to the chemical methods, we have soil washing techniques, then immobilization techniques, and encapsulation techniques. So I will be mostly focusing on the chemical methods in the presentation. That's also a part of research that I'm doing at my current university. And in addition to the physical and chemical methods, we have the biological methods. So as the name says, biological methods mostly relates to phytoremediation, that is using some particular types of plants to remediate contaminated soils. And in addition to plants, it can also refer to the bioremediation in general, where we use some microorganisms, some living organisms to treat the soil and encapsulate the contaminants. So in all these methods, the primary aim or the ultimate goal is to reduce the further contamination and to fix the contaminants within the soil. So we can either fix them in the soil or we can remove them from the soil. So these are the two methods of soil or treating this contaminated soil. Either we try to remove the contaminants from the soil, or you try to fix the contaminants within the soil and reduce its availability to the plants and animals and the and prevent it from entering the food chain. Now we can quickly go through the major physical, chemical, and the biological methods. So I will not go into details because I know that there have been previous talks where some of these techniques were discussed in very detailed fashion. So when you come to the physical methods, one of the most popular method in physical treatment is thermal treatment. So as you can see in the figure, so in thermal treatment, the contaminants are removed by the evaporation technique. Okay, so we have some roads, okay, so which can be controlled to a particular temperature. So we can increase the temperature of this road. These are heating rods actually. So by heating the roads to right temperature, we heat the surrounding soil, and the contaminants in the soil becomes vapor. They vaporizes, and these vapors are collected in a tube and it goes to a vapor treatment building. And so in this building, so this vapor which is collected has lots of chemicals and contaminants in it. So that is treated and the contaminants are removed from the vapor. So although this is a good technique, it's not sustainable, because sometimes even if we do some treatment for the vapor, it's not 100% foolproof. So once we complete the treatment and then allow this vapor to mix with the atmosphere, there are chances of causing air pollution. So therefore, we do not consider this thermal treatment process as sustainable process. And then Another important area of treatment methods is the chemical methods. And as the name suggests, in this method, we actually treat the soil with some chemical compounds. So what happens during this treatment, some chemical processes takes place due to the reaction between the soil and the chemical that we have added. And using these chemical treatment methods, we try to restore the natural chemical balance in the soil. So we mentioned that when a soil is contaminated, it can actually lose its natural balance. So some of the macro and micronutrients may become deficient. And by using the appropriate chemicals, we try to restore the chemical balance in the soil and make it nutritious and fertile. And we have to regularly do this chemical method. It's not just one time method. We may need to do it repeatedly until we ensure that the detoxification process is complete. And so when you talk about chemicals, it's important to note that we cannot add any chemical, that we prefer into the soil. There are some, like we can say, some regulations and guidelines. Okay, so here in America, we have this EPA, that is Environment Protection Agency. And when you talk about soil amendments, we can only use those chemicals or compounds that are EPA approved. Okay, because some of the chemicals that we may choose for soil treatment may also have some harmful contaminants in them, and that itself can be toxic to the soil. So we may be doing further damage to the soil rather than protecting the soil or remediating the soil. So in order to avoid such kinds of dangers, the EPA has tested and approved some particular products that can be used as soil amendment. So some of the EPA approved materials used as soil amendments are the municipal biosolids, animal manures and litters, sugar beet lime, and also we have wood ash, that is the byproduct of burning wood at a very high temperature. Then the coal combustion products such as the coal ash, coal fly ash, then lime products, composted biosolids, and a variety of other composted agricultural byproducts, and the traditional agricultural fertilizers. So this is a long list, but this is important because even when we do research, we have to look at these EPA approved materials. We have to ensure that when we try to consider a new compound or a new material as a soil amendment, we must ensure that its environmental properties or its toxicology properties meet with the EPA guidelines. So we have to ensure that the toxicity levels in those chemical compounds are below the permissible limits. So mostly the chemical methods, so we mentioned that the chemical methods are used to ensure that detoxification is proper and complete in the soils. So also, I can say in other words that chemical methods are mostly suitable for in situ immobilization of toxic metals in the soils. So rather than for nutrition restoration, chemical methods, some of the chemicals, especially the fly ash or biosolids, these types of chemicals are suitable for immobilization of toxic metals in the soil. So how does that happen? It happens by chemical fixation. So that happens by when you add the reagents or materials into a contaminated soil, they undergo some reactions and form insoluble low toxic matter in the soil. So as you can see in this figure, this is a picture showing a lead contaminated soil. Okay, so on the left side we have the contaminated soil with easily leachable lead, and then you add an immobilizer or a material or a reagent into the soil. And what happens is that these reagents will have some specific surface properties. Okay, so these surface properties makes it a very good adsorbent. Okay, it attracts the lead part metal or the lead ions present in the soil, and the lead ions gets fixed onto this immobilizing agent. Okay, So as a result, when this agent fixes the lead onto its surface, its leachability reduces. Or we can say, in other words, we are manipulating the bioavailability of the lead. So for example, let's say initially that we have a soil with a contamination of lead concentration of, like, say 200 ppm, just a random number I'm taking. And now you added an immobilizing agent. So what happens? These lead ions are going to get absorbed onto the agent, the surface of the agent. It can be either adsorption or absorption. So when you say adsorption, AD, that is adsorption, it's happening at the surface level. Okay, they get attached to the surface of the agent, the reagent. So after the immobilization, still we have the 200 ppm lead in the soil, but they are fixed now. They are not anymore available, or they are not in a leachable state. So that means now the plants cannot absorb these toxic chemicals. Okay, so we are reducing or manipulating the bioavailability of these toxic chemicals by adding some specific reagents or materials. So we can say that this technique of using chemical reagents efficiently alleviates the risk of groundwater contamination, plant uptake, and also exposure to other living organisms. So that is one advantage of an immobilization, in situ immobilization technique. And we also have some extraction and separation techniques. So these techniques basically, uses some solvents, organic solvents. So an organic solvent is an extracting agent, so which is mixed with the contaminated soil. So what happens is that these agents actually removes the contaminant from the soil. Okay, or the impurities in the soil are removed. uh, Especially it happens by the principle of gravitational pull. Okay, so this is, I'm not going into details of these techniques. So this is another important area of soil remediation, which is extraction and separation technique. So here it's not fixing in the soil but removing from the soil. And then we have the bioremediation, which is, I would say, a beautiful method for soil treatment. Why I call it beautiful is because it's one of the most sustainable ways of removing soil contamination or treating a contaminated soil. So here we use different types of organic like materials, like we can use microorganisms, as I mentioned, like the microbes which are originally present in the soil, or we can develop new microbes by genetic engineering, microbes which can, specifically absorb some of, that means which can focus on a particular contaminant and absorb a particular contaminant. And also in bioremediation, we have the phytoremediation, where you use some types of plants to extract the contaminants from the soil. And again, so we have another talk on phytoremediation in this series, therefore I'm not going into details. Then we have the electrokinetic remediation. I think yesterday Dr. Nikhil gave a lecture or a talk on electrokinetic remediation. So in general, EKR technology is used for migration, separation, and removal of pollutants in soil. So this is one of the most, I would say, recently advancing areas of soil reclamation technology. Basically, there are two reasons. One is that it is cost efficient, and also it has the minimum environmental impact, so which is very important. So electrokinetic remediation has very minimal environmental impact, and therefore it is highly recommended. So there are different types of methods for in electrokinetic remediation, that is electroosmosis, electromigration, or electrophoresis. So basically the EKR remediation in initial days, when this electrokinetic method was developed, it was considered as a soil stabilization technique. So it was used for dehydrating sediment. For example, if you have a highly saturated clay, using electrokinetic method, we could remove the water. Also, we could use it as a strengthening method, like for stabilizing the soil foundations. But over the last few decades, there has been a great advancement in this technology, and ECAR has been widely used in the removal of a variety of pollutants, including the heavy metals or organic pollutants, as well as some nuclear or radioactive substances, for example uranium. And therefore it's further advancing, I would say, and it has a lot of future prospects. And lastly, I wanted to add this slide also, where we have solid waste treatment. So similar to contaminated soil treatment, we also talk about a solid waste treatment, because we said that the industrial waste, okay, the residues or byproducts are a major cause for soil contamination. So before we discard any type of industrial waste into the soil, we must treat them properly. So when you say treating the waste, we mean stabilizing the waste or remediating the waste. That is removing the toxicity from the waste by physical or chemical or biological methods before we dump them into the soil. So by proper treatment, we can reduce the hazardous levels up to the environment, and also we can minimize the contamination. So now, so we talked about so many different methods of soil remediation, and I wanted to bring these four important methods in front of you, because these are the future perspectives for soil remediation, as per the scientists who work in this area of research. So one is electrokinetic remediation, and then we have phytoremediation, remediation with nanoparticles. That is one very advancing area of soil remediation. And then we also have biochar technology. So biochar is the we can say the residue which is produced after combustion of wood or biomass, and this biochar has specific surface properties which helps it to absorb heavy metals. So biochar, nanoparticle technology, phytoremediation, and electrokinetic remediation, these are the future perspectives, basically because they are the most sustainable ways of soil remediation. Now, here, I would like to focus on the biochar aspect of soil remediation. So, similar to biochar, we also have some other byproducts from industry, such as red mud or wood ash, steel slag, etc. So, all these products or industrial byproducts are inexpensive, right? Because they are basically waste materials. So they are zero cost materials. And also these types of byproducts are produced in enormous quantities in the industries. Every day, or we can say every month, piles of this waste goes to the landfills. So in recent research, scientists are trying to recycle some of these byproducts and find alternative applications for these value added materials. And one such application for these byproducts is the soil contamination remediation. So especially from studies, it is found that biochar shows very high efficiency to remediate multi-metal contaminated soil. So that means not just one metal, but biochar can concentrate on multiple metals at a time and remove those different types of metals from a contaminated soil. So this can be considered as a very preferable option. First thing, it is inexpensive, and also it is easily applicable to large quantities of contaminants from various sources. So as you can see in this picture here on the right side, so here we have a cross section of a biochar. So you can see that the biochar has a very highly porous structure. So it has a lot of macropores. And due to this, the surface properties, the specific properties of biochar, it also has some specific metals or elements attached to its surface. So when the biochar comes in contact with a contaminated soil, it actually adsorbs or it attracts the contaminants through different means, and the contaminants get fixed onto the surface of the biochar. Okay, so it helps to reduce or immobilize heavy metals. And in addition to the immobilization of heavy metals, biochar has other advantages. One is that it acts as a soil nutrition. So if you all remember, like we used to put ash, right? Simple wood ash into the soil as a nutrient. So similarly, so that is a natural byproduct, but there are recent technologies where we can manipulate the properties of a biochar. So we can make biochar for specific applications. So by manipulating its surface properties and its chemistry. Okay, so this biochar, it can immobilize the toxic metals. It can, provide nutrients to the soil, and also due to its high surface area, it helps in better air circulation, water infiltration, and also proliferation of soil microbes. Okay, and another area which I want to focus here is the carbon sequestration. So we know that these days across the world there are hot discussions about the increasing greenhouse gases and global warming, right, which is due to the increasing CO2 concentration in the atmosphere. And scientists are seeking for new materials which can actually absorb the carbon from the atmosphere and fix it. So that's technology is called carbon sequestration technology, and biochar is one of the promising materials which can be used for efficient carbon sequestration. So in total, biochar, it's a complete package. It has a lot of advantages. And in Canada, we have a lot of new startup companies which produce biochar for different applications. It can be for agriculture or for construction industry. Biochar can be used as a cement in concrete, and it can be used for contaminant soil remediation, for stabilization of industrial waste, etc., etc. And so I mentioned that the surface property and the chemistry of the biochar helps it to absorb the toxic elements, right? So there are actually a different number of or different types of, chemical actions that occur on the surface of a biochar. So one is surface complex formation. Then there is ion exchange and electrostatic attraction between the biochar and the toxic elements present in the soil. And there is pore filling. So some of the elements gets filled into the pores, they get absorbed into the pores of the biochar. And also some chemical reactions lead to precipitation of the contaminants. For example, if there is cadmium as a contaminant, and if the biochar has carbonate in it, then it can lead to precipitation of the cadmium as cadmium carbonate. And what happens is that once the cadmium gets precipitated, and that compound is mostly insoluble in water, and therefore it gets fixed into the biochar and it becomes non-bioavailable. So that's about this picture. It just shows how the toxic elements are getting fixed into the biochar by the different chemical processes. And now, at this point, I would like to give you some insights into my research at UBC. So I've been conducting some independent research for the past more than 2 years at UBC. And as you can see in this figure, I was mostly concentrating on utilizing some solid residues from the Canadian pulp and paper industry as a soil amendment. So in Canada, we have a lot of pulp and paper mills. So basically, these industry produces the pulp and then makes paper out of it. So the pulp, as you know, the pulp is produced from wood. Usually, we use some, wood chips to make the pulp. And in these pulp mills, we have power boiler units. So these power boiler units basically generate electricity, which helps to run the entire unit 24/7. And these power boiler units, in those boiler units, the waste wood is used as a fuel. And what happens, the wood is burned in a furnace at very high temperature, and from the steam that is produced, it generates electricity. So during this combustion of the waste wood in the furnace of the boiler, it generates a lot of solid residues. So as you can see in the picture, I have just put the pictures of the different types of residues, solid residues that is generated in a pulp mill. So three important, not two, there are three important residues that comes from the power boiler unit. One is the precipitator fly ash, the one shown here. It looks just like cement, the Portland cement. It's very fine talc. And then we have a multi-cyclone fly ash. So these are the two types of fly ashes which are produced in the power boiler units of pulp mill. And then we have basically the bottom ash. Bottom ash is something aggregates which settles down at the end of the at the bottom of the furnace. So minimum of 1 million tons of ash is produced every year in Canada, and these industries are actually disposing or dumping these waste in their landfills at a cost of about $20 to $50 per ton. So therefore, it's always very important for this industry to find a way to recycle these waste products and divert them from the landfills and make some revenue out of it. So in my research, I was trying to recycle these three important waste products, that is the bottom ash and the fly ash, and find some alternative applications for these types of waste. And so first, I started with the precipitator ash. So this, as I mentioned, this fly ash is very much similar to the coal fly ash, the class C coal fly ash with a very high calcium content. And I tried to find some applications for this ash in road stabilization, which was successful. We constructed a small test road section in the last summer, and it's going good. And also, I wanted to bring another area of project which is more relevant to the theme of this series or this FTP, and that is a utilization of this waste for stabilizing a wildfire impacted soil. Okay, so the overall theme or the overall goal of my research was to find some value to this waste, so add some value to this waste product and then use them as eco-friendly soil amendment. Okay, so it's kind of a waste management strategy, and also at the same time it is helping as a soil amendment or soil stabilization technique. So the first important step was to do the laboratory analysis of the ash. So whenever we want to utilize any material for a particular application, we need to test that material and understand its properties to make sure that it is suitable for the particular application. So here we can see the two types of ashes and the images taken with the help of a scanning electron microscope. And we looked at the chemistry of these ashes and we found that it has very high calcium, silica, and alumina. So that means it is good for cementing purposes. And more importantly, we needed to look at the toxicological properties. So as I mentioned, sometimes when you choose some material or product for soil amendment, the toxicity levels in that material, if it's high, that can be dangerous. So it is important to conduct a toxicological study and make sure that all the elements are within the permissible limits. So here we have found out the concentrations of different elements or metals and compared with the standard or guidelines for the water quality test, especially standard for agriculture and standard for aquatic life. And we ensured that all the toxic elements are within the permissible limits. And here I have just brought in some high resolution images of the multiclone ash, which is the second type of ash produced in the power boiler, you can see that this ash has a structure very similar to that of biochar with very large pores in it. So a multiclone ash is can be used as a soil, a contaminant remediation treatment method. And so we are looking at wood ash as a soil amendment for wildfire impacted soils, right? So in Canada, every summer, when the peak temperatures go as high as 40 degrees, we have several incidents of wildfires, which are sometimes fatal. And these are some images during the wildfire and after the wildfire. You can see that the entire vegetation is removed, it is destroyed, and the topsoil is now completely burned. So depending on the severity of the fire, sometimes only the top few centimeters of soil will be destroyed, and if it is very severe wildfire, it can go deep down into a few 10 or 20 centimeters of soil. And in this project, what we did, we went to a site where where there was a wildfire, and we collected some burnt and unburnt soil samples, and we compared their properties to understand what are the impact of wildfire on the soil. So we looked at the physicochemical properties, and and just from the SEM image itself, we can see that this is for the unburned soil, and this is for the burnt soil, that is the soil after the wildfire. We can see there are some wood ash particles, that is a remnants of the vegetation, and also some weak aggregations are formed here. And so we did some important geotechnical tests, okay, on the burned and unburned soils. And further, we treated this burned soil with the precipitator ash in different concentrations like 5%, 10%, etc. So here we also try to limit the maximum percentage of the ash we use, because as I mentioned, this wood ash also has some toxicity, although it is not high, it has some toxicity. So we always try to minimize the amount of ash that we use for treatment. And after the treatment, we found that the aggregate stability of the soil has improved, because this wood ash has cementing properties. It actually reacted with the soil and improved the stability of the soil. And also, if you look at this figure, we can see that the treatment with wood ash has improved the water absorption capacity of the soil. So that's again another way of remediating the wildfire impacted soil. And here, these SLM images show some new compounds formed on the surface of the soil. So these are the cementing compounds or products, and they actually keeps the soil together, and also it encapsulates the toxins present in the soil. So after the wildfire, usually we can see that some toxic element concentrations are very high. So by stabilizing with a fly ash, what happens? These toxic elements gets encapsulated or fixed into our soil. And in order to ensure that this encapsulation has been done properly or detoxification has happened, we did a leachate characterization test on the treated and untreated soil samples. And as you can see here, this is the data for unburned soil and for burnt soil. You can see how much increment in some of the metals have happened after the wildfire. So that means toxicity has increased due to the wildfire. That means soil has been contaminated. And now, after treatment with the ash, you can see these are two different treated soils. And you can see that the concentrations of the toxins have drastically decreased. Okay, so this is the concentration in the leachate, or that means it is a leached concentration of toxins. So the leachability has substantially decreased by the fly ash treatment. Okay, so that's just some insight into my research. And just before concluding, just want to give you some more thoughts here. So the Environmental Protection Agency has categorized contaminated lands into different classifications or categories. And so when you have a practical problem, we need to look into the category where we are supposed to develop a solution strategy. So you look at the practical scenario, look at the type of contaminant, the level of contamination, and then you go for the proper selection of the contaminant remediation technology. And also, when you look at the contaminated soil, it's important to test the soil and understand the level and type of contamination. And if you can go to this particular site, you can see that the EPA has developed some advanced technologies for rapid testing of contaminated soil and understanding the level of contamination. And now I'd like to conclude my session. So just a few points that you can take away today. One is that it's very important to understand the sources and level of pollution. So that means sometimes I can give you an example again. So if you see that a soil is contaminated with cadmium and there is again about 100 ppm contamination, but when you test the soil, you understand that the bioavailability of the contaminant is only 50%. So if you have that information in advance, if you do some thought process in advance, then the level of remediation technology required can be minimized, and thereby we can reduce the expenses for these kinds of remediation techniques. And it is important to select the appropriate technique for an appropriate contaminant and an appropriate soil. And more importantly, we should always look for eco-friendly and cost-effective contamination remediation techniques. And as a researcher, we should always look for the lab to field transformation. So in the lab, we can do any kinds of research. We can do any kinds of chemical treatments to the soil, but always we need to think about the practical scenario and the potential limitations of these different technologies. And last but not least, sustainability should be the key factor, because I always end my slides with this word that we engineers must challenge ourselves to do the right project and do it in the right way by incorporating sustainability. Whatever we do should be, focusing on the protection of our environment and protection of our ecosystem. These are the few of my references, and thank you for listening.